Gases and chemical reactions. So some reactions produce gases. Other reactions may have gases as their reactants. And we can do stoichiometry with reactions involving gases. The amount of gas is often specified in terms of its volume at a given temperature and pressure. And from that information, we can use the ideal gas law and calculate the number of moles. Because in stoichiometry, we were interested in the number of moles, right? Our path generally was grams to moles to moles to grams. You have to get to moles. So this is just adding a little twist. If your starting substance is a gas and you're given pressure, temperature, and volume, then you have to calculate the moles that way. And so the ideal gas law allows us to do that. The amount of moles will equal the pressure times the volume divided by the ideal gas constant times the temperature in Kelvin. And then we continue on as normal using the stoichiometric coefficients to convert to other quantities in the reaction. So here's an example. 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? Well, here we have an equation. So what we're doing here is we're combining gas law stuff with stoichiometry. The question that we're being asked is how many grams of this stuff? And we're given information about the oxygen. It says 4.58 liters of that, 745 millimeters of mercury, and 308 Kelvin. So even if you're not sure what direction you're going, pull the numbers out and write them down so that you can see a little more clearly what you've got. Well, this is a volume, right? And this is a pressure, and this is a temperature. We've got information about oxygen, and they're asking us about something else. We need to use this balanced chemical equation to relate those two. And so the center of all of our problems like this is going to be moles to moles. Here at the end we have grams, because this is the question, how many grams? So we want grams at the end, but what are we starting with at the beginning? We've got pressure, volume, and temperature. So we've got P, V, and T. Can we use that to find the number of moles of oxygen? PV equals nRT, right? Ideal gas law. So if we have the pressure, the volume, and the temperature, because there's 4 variables involved with gases: pressure, volume, temperature, and number of moles. So if we have pressure, volume, and temperature, we can calculate the number of moles. Once we have the moles, then we can convert to moles of the other thing and grams of the other thing. Are these units that we're given all good units for an ideal gas law calculation? No. Which one's not? The pressure's not right, because the R is 0.0821 liter atmospheres per mole Kelvin. We've got our temperature in Kelvin, we've got our volume in liters. The pressure has to be in atmospheres or the equation doesn't work. So we have to convert that. So 1 atmosphere for every 760 millimeters of mercury. And that's not going to fit, is it? $745 divided by 760. So 0.980. 0.980 atmospheres. So first we need to calculate the number of moles of hydrogen, and then we need to calculate moles of silver oxide and then grams of silver oxide. So I'm going to start way over here. N equals PV over RT. So that's the pressure, which we just said was 0.920 atmospheres, times the volume, 4.58 liters, divided by R, 0.0821 liter atmospheres per mole Kelvin, times the temperature, 308. So 0.980 times 4.58 divided by 0.0821 divided by 308. So N equals 0.177. I'm just going to throw in an extra digit there. It's here. It was, I don't feel like doing that today. We'll just leave it at that. 0.177 moles of oxygen, not hydrogen. Moles of oxygen. Did you get that number on your calculator? Make sure you're being careful with your numbers in the denominator there. If you got a really big number, then you have a calculator glitch. So from moles of oxygen, we want to go to moles of silver oxide, and then to grams of silver oxide. And then we put our units in so they cancel out like we want them to. So moles of oxygen cancel, moles of silver oxide cancel. What's the relationship between moles of silver oxide and moles of oxygen? Balanced chemical equation. What number is in front of Ag2O? A 2. And in front of oxygen? There's nothing, right? So that's a 1. What's the relationship between grams and moles for silver oxide? Well, we need to calculate that, don't we? That's the molar mass. So 2 times the mass of silver, which is 107.9, and 1 oxygen. So 107.9 times 2 plus 16, I get 231.8. So 231.8. So now I can calculate 0.177 times 2 times 231.8 equals 82.1 grams of silver oxide. Any questions? So here we're pulling multiple concepts together. If you're struggling with some of the individual parts, go back and figure those out first, because you can't put stuff together that you don't understand. So we're doing stoichiometry, we're doing a gas law, and part of stoichiometry is calculating molar mass, and part of the gas law is converting units. So the snowball is growing. No questions about that one?
What was the answer that you got for N?
For N was 0.177 moles. And then I converted that to moles of silver oxide and then to grams.
Grams to moles.
Grams to moles to moles to grams. This time, though, we're not starting with grams. PVT to moles to grams just doesn't have the same ring to it, does it?
No.
This could also be switched around. They could ask you, well, if you had this many grams of silver oxide, what volume of gas or what pressure of gas would you get at the end? Okay, so from calculating moles of gas through the stoichiometry, then you can use the ideal gas law to calculate one of the quantities that's not given. Standard temperature and pressure. That's a state of, that's abbreviated STP for standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. Now, standard pressure being 1 atmosphere makes sense because, you know, most places the atmospheric pressure is going to be 1 atmosphere or very close to it. Why did they pick 0 for the temperature? I think the reason they did this is because 0 degrees Celsius is a very easy temperature to obtain without any equipment or anything. All you need is a big container, some ice, and water. So if you want your reaction to occur at standard temperature of 0 degrees, you just have to put it in a container and submerge it in ice water, and there you go. You've got 0. So if that helps you remember, because, you know, what is standard temperature again? 0. Ice water, or 273 Kelvin. So let's calculate the volume of 1 mole of gas at STP. So we're given STP, so that's standard temperature and pressure, and the volume of 1 mole. Well, PV equals nRT. So if we divide by P on both sides, we get volume equal to nRT. So it told us that N was 1, so 1 mole, and R is always the same, liter atmospheres per mole Kelvin. And what's the temperature at STP?
273 degrees.
273 Kelvin. We have to use the Kelvin, because if we put in 0, then our volume of gas would be 0, and that's impossible. And the pressure is 1 atmosphere. So you calculate that, and you get 22.4 liters. I didn't actually have to calculate that because I knew what it was. It's called the molar volume of a gas. We've talked about molar mass. Molar mass is the mass of 1 mole. Molar volume is the volume of 1 mole. Now, the volume of 1 mole of gas is going to depend on the temperature and the pressure. But at STP, at standard temperature and pressure, the molar volume of a gas is 22.4 liters. That's the molar volume of any gas. It could be hydrogen gas, it could be xenon gas. Xenon has a molar mass of 131. Xenon atoms are much bigger than hydrogen molecules. How can the volume of that 1 mole of that gas be the same as 1 mole of hydrogen? There's so much empty space between that the size of the particles doesn't matter in terms of the volume of the gas. So any gas at STP has 1 mole has a volume of 22.4 liters. And so that ends up being a really useful conversion factor. 22.4 liters per mole. It's only true at STP. But we can use that and simplify some calculations. That's really funny. I was comparing helium with xenon, but I'm hydrogen. Here's helium and xenon. And so here we see that the volume, here's representing 1 mole of helium. That's obviously not 1 mole of helium particles.
John.
And 1 mole of xenon particles, equal amounts, and they're occupying the same overall volume, even though the xenon particles are definitely larger than the helium particles. But that's because there's so much empty space that it doesn't matter. The thing that's different is the mass of this container is going to be less for the helium. So a mole of helium only weighs 4 grams, a mole of xenon weighs 131 grams in the same volume under the same conditions. So if you had a balloon full of xenon gas, would it float? No, it would sink like a rock. Yeah.
Would that even sink in water?
No. No. It's still much less dense than water.
It's not around though, because it weighs several ounces.
Oh yeah, 22 liters of water weighs way more than 131 grams.
Yeah.
It probably weighs like a couple pounds.
Yeah, actually, 22.4 liters is a cube about this big. So you'd be hard pressed to carry that.
It'd be like carrying a large aquarium.
Yeah, a big aquarium. Super heavy. Okay, so here's another stoichiometry problem with gases in it. How many liters of oxygen at STP are required to form 10.5 grams of water? So the question is how many liters of oxygen, so question mark liters, and they're giving us that we want to make 10.5 grams of water. And the other little detail in there, not to be overlooked, at STP. So anytime you see at STP, think, maybe I can use that 22.4. So, our normal thing was grams, I'll do it up here because our normal mode was grams to moles to moles to grams. Hopefully you all have that down pat now. So at the end here, we want to find grams of water. But at the beginning, we don't have grams of oxygen. We have, no, I did that backwards, sorry. Stop me when I do that. We know the grams of water. That's where we're starting. That was backwards. We know the grams of water. We can calculate moles of water. We can calculate moles of oxygen. But we're not trying to find the mass of oxygen. We're trying to find liters of oxygen at STP. So 10.5 grams of water. And we're going to convert that to moles of water. And we're going to convert that to moles of oxygen. And then we don't actually have to use the gas law, ideal gas law, because this is at STP. We can go straight to liters of oxygen. And then we stick our units in so they all cancel out so nicely. I wish life was this simple. Maybe it is, and I just don't understand it. Because I know you guys probably don't think this is simple. So there's the units. How many moles of oxygen for how many moles of water? 1 mole of oxygen to 2 moles of water. And that comes from this non-existent number there and this number 2. Grams of water to moles of water. 2 times the mass of hydrogen plus the mass of oxygen, it's 18.02. And that's 1 mole of water. And then over here, liters per mole of oxygen at STP, 22.4. Now, if you did not remember or think to use that, you could stop there and calculate the moles of oxygen and plug it into the ideal gas equation and come up with the right answer. It's just easier if you remember 22.4. So 10.5 divided by 18.02 divided by 2 times 22.4. So that equals, we should have three significant figures here, 6.53 liters of oxygen. So to make 10.5 grams of water, we need 6.5 liters of oxygen at 0 degrees Celsius in 1 atmosphere. Any questions? That's the end of the chapter. I can pretty much guarantee you there will be a question like that last one on the exam.